Since humanity first learned to look up and question the night sky, our solar system has been more than a scattering of distant lights. It has been a living, evolving structure, a cosmic engine shaped by forces older than Earth itself. What seems simple in textbooks, a star in the center, planets orbiting around it, a few moons, asteroids, and icy bodies, is in reality a dynamic and interconnected system forged through violent collisions, gravitational battles, and chemical transformations that have lasted for 4.6 billion years.
Hey friends, my channel is still very small and really needs your support. I am just learning, so I am also waiting for your comments below. Please let me know what to improve or what you liked. Please hit that like button, subscribe, and we will meet again.
At its heart lies the Sun, a massive thermonuclear furnace whose unimaginable energy sustains life on Earth and governs the behavior of every planet. The Sun's gravity dictates their motion, while its solar wind sculpts magnetic fields, strips atmospheres, and creates auroras on worlds as different as Earth, Jupiter, and even the distant dwarf planets. Its magnetic loops twist and snap, launching eruptions that can disrupt satellites and even electrical grids across Earth. The inner planets, Mercury, Venus, Earth, and Mars, tell the story of how small, rocky worlds can evolve in wildly different directions, despite starting from the same cosmic ingredients. Mercury is a scorched metal sphere with a gigantic iron core that makes up most of its size, a planet where daytime temperatures exceed 430 degrees Celsius, but nights plunge to deadly cold. Venus, once thought to be Earth's twin, turned into a hellish world when a runaway greenhouse effect transformed its skies into an opaque, crushing shroud of carbon dioxide and sulfuric acid. Earth alone found a delicate equilibrium that allowed oceans, atmosphere, and life to flourish. And Mars, now a cold desert, shows clear signs that it once had rivers, lakes, and perhaps even oceans. Its dried riverbeds, mineral deposits, and ancient deltas hint at a past that may have supported microbial life before its atmosphere thinned and its magnetic field vanished. Beyond them lie the giants, Jupiter, Saturn, Uranus, and Neptune, massive worlds that control the architecture of the entire solar system. Jupiter alone is so large that it influences the orbits of asteroids, redirects comets, and may have prevented the formation of a super-Earth near the Sun. Its immense gravity protects Earth by capturing or deflecting potentially deadly objects, yet it can also hurl others inward in complex gravitational dances. Saturn, with its magnificent rings, is a system in itself, home to moons like Titan, rich in organic chemistry, and Enceladus, which ejects water plumes from an ocean beneath its icy crust. Uranus and Neptune, the ice giants, contain exotic forms of water, ammonia, and methane under crushing pressures that create oceans of supercritical fluids and possibly diamond rain deep within their interiors. Between Mars and Jupiter lies the asteroid belt, not the chaotic debris field shown in movies, but a vast region where bodies are separated by hundreds of thousands of kilometers. These ancient rocks contain some of the oldest material in the solar system, remnants of the building blocks that never merged into a planet because Jupiter's gravity prevented their union. And farther out, in the Kuiper Belt and beyond, icy worlds like Pluto, Eris, and countless comet nuclei preserve the primordial chemistry of the early solar system, drifting on the frontier where sunlight grows faint and time seems slower. The solar system is not static, it is alive, shaped by gravitational tides, magnetic storms, chemical cycles, and cosmic impacts. Every planet, moon, and asteroid carries fragments of an ancient story written long before humans existed. And as our spacecraft push farther outward, we continue to uncover chapters that challenge everything we thought we knew about our place in the universe. Jupiter, the largest and most influential planet in our solar system, is far more than a colossal sphere of swirling gas. It is a cosmic cornerstone, a gravitational architect, and one of the primary reasons our planetary system looks the way it does today. Its staggering mass, more than twice that of all other planets combined, allows it to shape orbits, redirect asteroids, absorb comets, and even influence the formation of worlds billions of years ago. To study Jupiter is to study the fundamental forces that shaped Earth itself. Scientists believe that Jupiter formed incredibly early, only a few million years after the Sun, giving it enough time to dominate the distribution of material within the protoplanetary disk. One leading theory, the Grand Tack hypothesis, suggests that Jupiter may have migrated inward toward the Sun before reversing course due to gravitational interactions with Saturn, sweeping up planetary embryos and sculpting the inner solar system. Without this migration, Earth might have been smaller, Mars might have been a super-Earth, and Venus could have developed under entirely different conditions. Jupiter's role as both protector and threat became clear when astronomers observed how efficiently it captures or ejects long-period comets. Its gravity can pull an icy wanderer inward, fling it into the depths of space, or smash it apart, as seen in the dramatic 1994 impact of comet Shoemaker-Levy 9. The resulting explosions created fireballs larger than Earth and left scars in Jupiter's atmosphere that lasted for months, vivid reminders of the planet's immense power. But Jupiter's influence extends far beyond the occasional collision. Its magnetic field is the strongest of any planet, a massive bubble of charged particles that stretches millions of kilometers into space, creating deadly radiation belts and generating auroras far more powerful than those on Earth. The Juno spacecraft has revealed that Jupiter's interior is even stranger than expected. Rather than having a simple solid core, Jupiter appears to contain a fuzzy, partially dissolved core, where rock, ice, and metallic hydrogen mingle under crushing pressures and temperatures hotter than the surface of the Sun. Metallic hydrogen, an exotic state in which hydrogen behaves like a liquid metal, exists only under extreme conditions and may be responsible for Jupiter's extraordinary magnetic field. The planet's atmosphere is equally extreme. Its colorful bands are massive jet streams that dive thousands of kilometers deep, and its storms are towering structures with persistent lightning flashes many times more powerful than lightning on Earth. The Great Red Spot, a storm larger than Earth itself, has raged for centuries, shrinking and expanding as if the planet were breathing. Surrounding Jupiter is a miniature planetary system of 95 known moons, each with its own environment, history, and mysteries. Io, the most volcanically active body in the solar system, erupts with lava geysers that reach hundreds of kilometers into space. Europa holds a vast global ocean beneath its icy crust, an ocean that may contain more water than all of Earth's oceans combined. Ganymede, the only moon with its own magnetic field, displays brilliant auroras that shift across its surface. And Callisto, ancient and heavily cratered, preserves 4 billion years of history untouched by internal geology. These moons are not merely satellites, they are worlds, each capable of rewiring our understanding of planetary evolution, chemistry, and even biology. With upcoming missions like NASA's Europa Clipper and ESA's JUICE preparing to explore these moons in unprecedented detail, Jupiter stands at the center of the next great chapter in human discovery. Every orbit, every storm, every moon reveals a new clue about the forces that shaped our solar system, and perhaps about the conditions that could support life elsewhere in the universe. Across the far reaches of our solar system, beyond the warm glow of the Sun, a new frontier is emerging, made not of deserts or mountains, but of hidden oceans, frozen crusts, and worlds that overturn everything we thought we understood about planets. Enceladus, Titan, Europa, Io, Ganymede, and Callisto are no longer distant points on telescope photos. They have become the most compelling scientific destinations of the coming century. Together, they reveal a profound truth. The solar system is far more active, diverse, and chemically rich than early astronomers ever imagined. Each of these moons, some small enough to fit inside a major US state, contains clues that reach beyond planetary science. They suggest that life may not be a rare cosmic accident, but a natural outcome wherever water, energy, and chemistry persist over time. Enceladus, once an overlooked icy world orbiting Saturn, is now one of the strongest candidates for extraterrestrial life. Beneath its fractured crust lies a warm global ocean that vents water vapor, salts, and organic molecules into space. These geysers act like cosmic samples, allowing spacecraft to fly through them and collect material without drilling into the surface. Their chemistry hints at hydrothermal vents on the seafloor, similar to the environments that may have sparked life on early Earth. Enceladus challenges the idea that life requires sunlight or continents. Instead, it suggests that water, heat, and time might be enough. Titan, large and enigmatic, presents a completely different vision of habitability. Its thick nitrogen atmosphere and orange haze make it unlike any other world in the solar system. Rivers and lakes of liquid methane carve valleys and coastlines that resemble Earth, yet they form in an alien chemistry no human has ever experienced. Beneath Titan's icy crust likely lies another ocean of water and ammonia, creating a dual-layered world where organic chemistry thrives above and a potential habitat exists below. Titan expands our definition of what a habitable world might look like, showing that life's building blocks can flourish even under conditions unimaginably different from Earth's. Europa, gleaming under Jupiter's intense radiation, stands as one of the most intriguing targets of them all. Its cracked, icy surface hides a global ocean deeper than all of Earth's combined, warmed by tidal forces that may drive hydrothermal activity. Europa's shifting ice and occasional plumes suggest a restless world beneath the surface, one that may hold ecosystems powered not by sunlight, but by internal heat. The upcoming Europa Clipper mission will scan its surface, analyze its chemistry, and study its plumes with unmatched precision, perhaps bringing us closer to answering a question older than civilization. Is life a cosmic exception or a universal pattern? Beyond Europa, the other Jovian moons continue the story. Io's relentless volcanism proves that geological heat can thrive even in regions far from the sun. Ganymede, with its magnetic field and layered oceans, behaves more like a frozen planet than a moon. Callisto, ancient and heavily cratered, preserves the untouched history of the early solar system. Its surface a frozen chronicle of impacts billions of years old. Together, these worlds create a picture utterly unlike the dead solar system once imagined. They reveal oceans in darkness, volcanoes on ice worlds, methane weather cycles, and complex chemistry hidden beneath frozen crusts. And beyond science lies a larger truth. These moons are the next great human destinations. Missions like Dragonfly, Europa Clipper, JUICE, and future probes will not only return data, they will push our technology and our imagination further than ever before.